In the last video, we were here, and the next example, example 2, is left as an exercise for you. So in this video, we start with the page with the title "Falling Against Air Resistance" or "Fluid Resistance" at the top of the page. The word fluid means liquid or gas. Liquid or gas. For a free-falling object in vacuum on the Earth, it has an acceleration of 10 meters per second squared. The speed keeps on increasing forever. How will the motion look like if air resistance is present? First of all, air resistance is a force which is opposite to the motion of the object. And furthermore, it is not simply a constant, but it depends on the speed of the object. You can experience that by holding an umbrella. If you try to face the umbrella forward and you run as far as you can, you'll find that as you run faster and faster, the resistance on the umbrella gets larger and larger. So as speed increases, air resistance also increases. So let's look at this ball falling down. Since it's got motion, it's got air resistance. Note that if there is no motion, there will be no air resistance. So the net force here will be the weight minus the friction from air, F air. Okay, friction from air. And then how about the acceleration? It will be the net force equals ma, Newton's second law. With that, we can write down W minus air friction equal to ma. So therefore A equals to W minus F air divided by m, or equal to G minus the friction over mass. Okay, so let's look at the falling bit by bit. Now suppose the ball is just released. We've got a 2 kg ball, very big indeed, and initially the speed is 0, so the air resistance is also 0. So the net force should be equal to the weight, 20 Newton. So this should be the net force, 20 Newton. So therefore, the acceleration should be 10 meters per second squared. Okay, so here when released, velocity is 0, therefore air resistance is also 0. And then the net force acting on the object is equal to mg, okay, acting downward. Downward. Next, as the ball gains speed, the friction increase. Say it increases to 4 Newton per second. Okay, as the speed increases, So speed increases, so air friction increase, say, to 4 Newton. Okay, then the net force will be 20 minus 4, which is 16 so many newtons, and the acceleration will be smaller, and this time it becomes, say, 8 meters per second squared. Okay, because the net force is 16 divided by 2 give us 8. So this is the acceleration. So if you see there's still net force acting on it, so it also accelerates. So at the X stage, the speed still increases. Speed still increases. So increases, and the friction on air has increased to 12, and the friction on air increased to, say, 12 Newton, and therefore the net force will be decreased to 8 Newton this time, and hence the acceleration becomes, say, 1 meter per second squared. Okay, now summarizing this stage, after that speed increases and air resistance also oh, that's gone. Arrows, is it here? Also increases. Oh, thank God. Also increases. So the net force acting on the object, when the resistance increases, the net force must decreases. And because net force equals to mg minus air friction, F air, all right? So the A equal to the net force mg minus F air divided by m. So the acceleration becomes smaller. So therefore, the speed still increases, but at a lower rate. So the rate of increase will become lower and lower. What happened ultimately? So that is the final stage. So the air friction, air resistance increased to a stage when it is equal to the weight. What do we have? So the air resistance is 20 Newton, and the net force will be 20 minus 20, will be 0 Newton. So what happened to the acceleration? It will be 0. So it will be 0 meter per second squared acceleration. So the speed, what will happen to the speed? It will become constant. Okay, so let's put down these points. The air resistance keep on increasing in the last stage as the speed keeps increasing until what happens? The air resistance equals or balances the weight, equal and opposite to the weight. So the net force is equal to 0. And the object falls with we've got a special name, so falls with uniform velocity, so it won't stop, and we call this uniform velocity the terminal speed or terminal velocity of the following object. The air resistance does not increase anymore afterwards. So let's look at this point to make clear. When the air resistance increases to a point that equals the weight, the object will fall with constant terminal resistance. And the same thing happened for an object falling in oil, falling in water. A foot is the fluid friction is gone. What happened? Maybe I sort it out next time. Let's take a break.